Very good evening to all of you, dear participants. So we are happy and we are very excited to have Sir with us, and he'll be giving the sessions today. So today it is the day 2, and I welcome you all for the day 2 and session 3, and which I know many of you have been looking forward to. So today's expert speaker, in many ways, actually we believe an institution in the field of civil engineering, and he needs no introductions, and because we all follow him and his work. And sir, I'm delighted to formally introduce you to our participant. Sir, this is Professor KVL Subramaniam, sir, Professor HAG in the Department of Civil Engineering at IIT Hyderabad. And his expertise lies in the behavior of concrete and masonry structures, rheology control and concrete 3D printing, alkali activated binders, geopolymers, cementitious material, past mitigation, fiber reinforced concrete, innovative construction technology, SHM, structural health monitoring, and many. And we cannot say in every aspect of the structural engineering field, Sir has the expertise. And prior to joining to IIT Hyderabad, he served as an assistant professor at the City University of New York. And also he was the research associate at NSF Center for Advanced Cement-Based Material, Northwestern University, USA from 1999 to 2000. So Sir has published over 259 publications, papers in the reputed journals, and Sir is having more than 5,500 citations, and he is the leader. He is the leads in research in the fiber reinforced concrete. If we can say the additive manufacturing techniques, we can say the 3D concrete printing, materials behavior, everything. And we also know, we all are aware, sir, your notable research contribution for the project on the world highest on-site 3D printed military protective bunker, sir, at 11,000 feet in Leh Ladakh in 2025, which is developing a specialized concrete mix resilient to extreme high altitude conditions. So we are truly honored, sir, and privileged to welcome you, and would like to express our gratitude for your valuable time, sir.
Sure, thank you.
And
Dr.
moreover, sir,
Susanta.
I should say that like when I was doing the PhD, I used to follow your papers and readings. And I don't know whether you can remember me or not. A few years back, I had interaction with you about my research, and that time when I talked to you, it opened up my mind. Many things, it opened up, and it happens when one of the finest mind you rarely get chance to interact with. Uh, so if it happens.
All right. Yeah. Yeah. So thank you, Dr. Susanta. Let me actually thank you for inviting me for this FTP. I do realize that the main topic of the FTP is not exactly in the area that I work in, but nevertheless, a few years back, I had worked on something that is related to seismic fragility. That was actually a need driven by the construction practice in India. So I think, I've always looked at formulating something from ground up, understanding the mechanics, and then of course applying it to the field. And in this particular case, if I just start sharing my screen, yeah, I think my screen should be loading up.
Yeah, it's visible, sir. Could you
Yeah,
please
yeah,
make it a full screen?
yeah, yeah, I'm just going there. Yeah. So, okay. So what I would like to present today is about vulnerability assessment of soft brick unreinforced masonry walls. And I'll illustrate this with the 2001 Gujarat earthquake. So that's basically a case study that I will be presenting. And the whole idea here is um, to understand what is the vulnerability of this particular form of construction. Now, why even look at this form of construction? The reason why I would even bother with this form of construction is because if you look at unreinforced walls, and perhaps be well, that is true. But if you look at 70% of our construction in India, it is basically what we call unregulated or non-engineered construction. And of that construction, a predominant stock of buildings is basically made up of unreinforced masonry walls. And these are used as load-bearing masonry. And then usually what is done is structure starts off as a non-engineered structure. People build with experience. They will stack up some masonry walls, put a concrete slab on top of it. That will be the temporary abode for some people. Initially, they'll start residing there. Then they start expanding on it by building floors above it. And if you actually look at our Indo-Gangetic belt, starting from, let's say, the north all the way up to the east, Kolkata, along the Gangetic belt, a predominant form of construction is load-bearing masonry. Now, the reason why we even got interested in this is because we wanted to understand the mechanics of brick masonry. And I'll show you in the subsequent slides that what we found of the kind of masonry that's being made in India is that it's of a very different form than what we were making in the past. And the masonry that we use, the brick that we use, and I've given it a title or label which I call soft brick. This has become very prevalent in India now. And this basically the mechanics of masonry that is made with this soft brick is very different than what we expect from regular masonry buildings. Now, regular masonry buildings, when we talk about masonry, like say stone masonry, the building block itself is very, very stiff. And you just use some mortar to hold together the building blocks, which are basically stone units. Or if you look at hard-fired clay bricks, those are again very stiff bricks, which are held together by mortar. But what we are finding increasingly in India now is the form of brick that's coming is the soft brick. And here the mechanics completely changes. So now, without further ado, what we wanted to do was assess the vulnerability of these non-engineered, unreinforced masonry structures made with soft brick. And I would like to use something because you would like to see if you can project forward what you've learned onto a larger scale, and therefore we use 2001 Gujarat earthquake as a case study. What are the issues and challenges when we come to looking at trying to predict the behavior building stock, if you look at it, is that particularly coming to masonry, the models for cyclic response of masonry made with soft brick, there are very few models that are available. And if you look at calibrated models, there are even fewer. Then, of course, when you and this gets into the deep end of seismic analysis, is that we need to be able to generate ground motions, and you need, I mean, an accurate generation of ground motions, especially if you're doing a case study specific to a specific region which has already experienced an earthquake, particularly where the ground motion records are very poor. And India is a case study in that, where you have very few ground motions that are available. Then, of course, we need to come up with some vulnerability assessment and check to see if what we've predicted is accurate, because then we can use it in other locations. So the overall methodology of assessing vulnerability would be bringing together all three things: modeling the material, having a good way of generating ground motions, capturing the variability in the ground motions, and then combining these two, the variability in the material behavior with the variability in the ground motions, to predict the risk or probability of failure or what have you. So now coming to introduction, masonry buildings are the oldest buildings. So these have been used. And if you look at masonry, it is a non-homogeneous material. It's not homogeneous because it's basically made up of two materials, brick and mortar, which are placed in a repetitive pattern. So what you get is a composite material. It's not a homogeneous material, where thankfully, of course, what we have is a repetitive pattern of joints that form between the bricks. Now, in India, like I mentioned before, more and more we are seeing masonry made with soft clay brick. And we are finding that a lot of our construction, almost 60% of the building stock is made up with this soft clay brick. Now, this is, let me just start off by showing you the nature of the problem that we have. This is the outcome or what happened after the Bhuj earthquake. So you see a lot of unreinforced masonry, a lot of it is load bearing. In this case, of course, this is a peculiar case or particular case of out of plane failure of masonry. But then you also, there are a lot of in-plane failures of masonry structure, and you see that this is just exactly what I was talking about. You see the masonry here, load-bearing masonry with a concrete slab, and this stands no chance against an earthquake. Now, this is again an out-of-plane failure where essentially the wall collapsed in a direction which is out of plane of the wall itself. But we also, there was a lot of in-plane failures also. You see this particular house here, again, masonry construction. You see the diagonal cracking here. Extensive damage in all this load-bearing masonry structures here. More of cracking in, more, excuse me, more cracking that you see here. This, of course, is a case of an infill where you have a reinforced concrete column where masonry is used as an infill. And even there you saw extensive cracking in the masonry unit. Now, so coming to the first part was basically trying to understand the behavior of masonry. What do we know about predicting the response of masonry, particularly under lateral loads? Typically, when we look at a masonry unit like what you have here, it's an assembly of bricks which are slapped together or put together, and they're separated by this mortar joints here. So the horizontal joint is called the bed joint. The vertical joints are called the head joint. So the bed and head joints are formed. We have a repetitive pattern of bricks that are held together by this mortar, and the mortar is what holds, is basically the glue that holds together these bricks. Now, it's a composite material because it's made up of more than one material. You have brick and mortar, and therefore, if you want to really predict the response of masonry, what becomes important is the relative stiffness of these two materials. The stiffness of the brick and the stiffness of the mortar play a very, very important role in determining the load response of the masonry. Now, most of the studies, if you look at the literature, come from stiff brick masonry. So what do we call stiff brick masonry? It's where this the brick unit, and the brick unit could be hard fired clay or it could be stone. This brick unit is extremely stiff. I mean, if it is made of stone, you know that it's a very stiff material, and you have a cement mortar or lime mortar that holds the stones together. Now, what happens when we want to predict the response of this is we need to understand the behavior of the brick, the behavior of the mortar, and the interaction between those two. How are these two materials interacting? Only then will we understand what are the stress states that are produced in these two materials, and that will then allow us to predict the failure that happens in this material. Remember, the failure in the masonry is going to happen because either the brick fails or the mortar fails. And that depends upon the stress state that is produced in either of these two materials under the action of loads. Now, if I want to take it one step further, one step further would mean that I consider the variabilities in the properties. When you do vulnerability assessment, what you're trying to do is you're actually trying to capture the effect of variabilities in the properties of the structure or structural element or the material, and also the variabilities in the ground motion. So because we were trying to do a vulnerability assessment, we had to have accurate material models for masonry, which are tuned to what we see in India, and of course, realistic simulation of the ground motions. Now, this is the background part of it. Suppose I take masonry, and this is what we typically call a stack bonded masonry. Here, what we have are bricks basically which are stacked one on top of the other, separated by a mortar layer. This doesn't happen in real life because you typically do not create a continuous vertical joint in masonry. So if you look, if I just go up one slide, you see what happens here. This is the what we call a head joint, and head joints are not continuous. They're usually broken up by a brick in between here. So but what is the purpose of this stack bonded masonry is it helps us understand the stress states that are produced in the masonry. Now, if I typically masonry is used as a compression member or used for carrying compressive loads or gravity loads, and most of the designs we see for masonry are for are gravity load based designs and stress based designs, which basically work on minimizing tension because masonry is very weak in tension. And the primary, if it is a load-bearing wall, the primary concern is the gravity load, which would basically be essentially produce a compressive state of stress in the masonry. Now, it's a composite material. Now, when you look at this, and what happens typically in stiff brick masonry is that brick is stiffer than the mortar. So the brick has a much higher modulus than the masonry. So what happens then? When I apply a compressive stress on this, the brick doesn't expand as much. The expansion comes about because of the lateral expansion, which we associate with the Poisson's effect. Because the brick is stiff, it doesn't compress as much and it does not expand as much. Now, whereas mortar is typically, when you're talking about stiff brick masonry, the mortar is actually softer than the brick, which means that the mortar would actually compress more and would also expand more in the lateral directions. Now, if I try to put these two materials together, when you put these two materials together, what would happen is the brick does not want to expand as much, and the mortar would actually be expanding a lot more. So in that case, but they cannot move independent of each other because they're basically bonded to each other at this interface. So what happens then? When you apply a compressive stress, and remember what I'm applying is a uniaxial compression. If you look at the stress state in the brick, you have, of course, the vertical compression, which is the sigma y in the brick, but then lateral stresses also develop. Lateral stresses are basically stresses which are in the perpendicular direction perpendicular to the applied stress, which is compression. And these stresses are developing in the brick. And similarly, stresses also develop in the mortar. So this is the mortar. You see the vertical stress here, but you also have these lateral stresses that have developed. The lateral stresses develop in the brick and the mortar because of these different properties of the material. The brick, if it is stiffer than the mortar, or if the mortar is stiffer than the brick, you will end up creating what we call a multi-axial state of stress in both materials, brick and the mortar, although the applied stress is purely uniaxial. So this is the complexity. When you're dealing with masonry, typically you're dealing with a very complex state of stress in the constituent materials, the brick and the mortar. And therefore, if we really want to model this, we need to understand what is the stress state that is produced in the two materials and be able to then understand which material would fail first. And both these materials are actually weak in tension. That's one thing we need to remember. And both these materials actually are what we call brittle materials. So both brick and mortar are brittle, which means that they are stronger in compression, weaker in tension. And ultimately, the compressive failures in both materials are essentially a crushing type of failure. Yeah, there was somebody who's raised a hand. I was wondering if there's a question.
So shall we address the questions at the last part of the
I'm okay with that. I just saw somebody they said they had a question. So
yeah, yeah.
fine. Okay, fine. So we'll take it at the end then.
Yes.
Okay. Right. So now let me show you the compressive behavior of mortar. Remember what I said about, sorry, going back here. We said both the brick and the mortar are what we call classically, they're essentially quasi-brittle materials, which means both brick and mortar will have a compressive strength which is higher than the tensile strength. Both materials are weak in tension and they are strong in compression. And because the properties of these two materials are different, although I apply a uniaxial compressive stress on the masonry, I end up producing a triaxial state of stress in the masonry. Now, when we look at compressive behavior of mortar, and you typically do a cylinder test or a cube test, this is what the compressive stress strain response of the mortar would look like. Now, what we did is we basically made two types of mortar, a weak mortar and a strong mortar. And I'll even explain the reason why we tried two different forms of mortar. What's important to see here is when we took the strong mortar is something that basically is a little cement-rich mortar. And you see that the compressive stress strain curve, it builds up to a peak and gives you a compressive strength of around 30 megapascal. And then the compressive stress, the residual stress or the stress resistance slowly decreases as I increase the strain. And you see the maximum stress is reached around 0.002. This is exactly what we expect from our concrete. Looks like a typical compressive stress strain response of concrete. What is important is this lateral strain. So this blue line here shows the lateral strain, which is basically the expansion that is produced in the mortar when as I'm applying the compressive stress. So we are applying the compressive stress on the cylinder and we are measuring how much it is expanding. So what you notice here is up to the peak, there is a little expansion. But you see what happens after the peak load. After the peak, there is a tremendous amount of expansion that is taking place. So this material expands a lot. It actually dilates a lot close to failure. Now, if you look at a weak mortar, so this is a mortar that we made, which actually was not as cement rich. So this is a weaker mortar. Its strength was lower. You can see the stress strain response here in the green line. And this is the lateral expansion. You can see that even this mortar actually has a good amount of expansion that is taking place as the material is failing. The actual failure of the material, if you look at the strong mortar, happens somewhere here. This is where the material completely crushes. And if you look at the kind of expansion that is produced before the material fails completely, it's a good amount of expansion that has taken place. Now, the Poisson's ratios of both of these motors are almost equal, whether it is a strong motor or the weak motor. One is 0.19, the other is 0.2. So the Poisson's ratio is basically the lateral strain that is produced as you deform it in the vertical direction. Now, remember one thing, that is Poisson's ratio is a property that is measured while the material is still linear elastic. So that's only valid up to about, say, 50% of the peak load. After that, when the material becomes nonlinear, we cannot have a Poisson's ratio measure. Now, if I actually normalize the stress strain curves of the strong and the weak motor, what we find is something that looks here. The weaker motor is actually has a very gradual decrease in the stress after the peak load, whereas the stronger motor, the decrease is very, very rapid. So it's basically, again, something very typical of concrete-like materials, where if you make them stronger, the material becomes more brittle. That's what you're seeing here. So when we went to the stronger motor, the material does become more brittle. Now, the reason for trying these two motors is very straightforward. Now, the stronger motor is what I would expect to get in the cities, where basically we are perhaps a little bit more conscious, we are using more cement, whereas the weaker motor is what you may expect to see in the villages, where the skimp on the cement, the quality of cement is not so good. So the compressive strength of the motor is also going to be much lower. Now, the brick that we sourced different bricks. What we sourced was a brick that had a compressive strength of 15.6 MPa. This is my strong mortar, which is 1:3, which is basically 1 cement is to 3 sand. And the weaker mortar is 1:6 mortar, where you have 1 cement is to 6 sand. And you can see the difference in the compressive strengths and the difference in the Young's modulus, which is the stiffness. Well, this is for the mortar. So you can see that when I made the mortar stronger, so when I went from the 1:6 mortar to the 1:3 mortar, it became stronger. Its compressive strength was much higher, but it also became stiffer. Again, this is expected from concrete-like materials. But notice what happens here. This is brick that we sourced. The compressive strength of the brick was 15.6 MPa. So that's not bad. And if you compare the compressive strength of the brick with the mortar, it lies somewhere between the weak mortar and the strong mortar. So that's actually not the problem here. Look at this, the Young's modulus. It has only 1 GPa stiffness. It's actually very soft brick. And this is typical of what we are finding of bricks in India today. But the bricks are strong. That is, they have a high compressive strength, but they have a very low modulus. That means they are very soft. So what is happening now is the story in India is flipped. Typically, when we talked about masonry, we would have bricks which are hard-fired clay bricks, which were very strong and very stiff because they're almost like ceramic. Or if you make masonry with stone is also very strong and very stiff. But here, what we are finding with the bricks that are now coming in India is that the bricks are strong. They're, adequately strong. They're 15.6 megapascal in compressive strength, but they hardly have any stiffness. They're extremely soft. So now we are going around building masonry with this brick, which is just 1 GPa in stiffness, and matching it or mating it with this mortar, which even if it's a weak mortar, which has only 8 MPa compressive strength, is 10 times stiffer than the brick. This is the story that we're dealing with. And now masonry that we're making in India, the story is completely flipped. Brick is soft and the mortar is stiff. Even the so-called weak mortars are 10 times stiffer than the brick. So what changes now? If you look at the way we are taught masonry and the composite action in masonry, we typically deal with stiff brick and soft mortar. That is, the brick is stiff, brick is much stiffer than the mortar. So what happens? The modulus of the brick is much larger than the modulus of the mortar, and the Poisson's ratio of the brick is actually smaller than the Poisson's ratio of the mortar, right? So basically, brick is much stiffer material. When you apply a compressive stress on it, it doesn't expand as much laterally compared to mortar. Now, what happens in that case? When I apply an axial compression on the masonry, now the brick, when you apply a compressive stress, it does not want to expand as much. And whereas if you apply a compressive stress on the mortar, because the mortar, the compressive stress is the same in both materials, and because the Poisson's ratio of the mortar is much higher, the mortar wants to expand more. Now, when you match these two, when you basically force them to move together at this interface, what happens? You basically develop a triaxial state of stress where the brick goes into biaxial tension. It's being pulled apart in two directions, and a uniaxial compression in the vertical direction. The mortar is actually in a state of triaxial compression. So why? Because the mortar wants to expand more, and its expansion is being checked by the brick, which is stiffer and has a smaller Poisson's ratio. So the mortar is nicely sitting in a triaxial compressive state of stress. Whereas if you come to the case of the soft brick, the story completely reverses. Now what we have is the modulus of the brick is smaller than the modulus of the mortar, but the Poisson's ratio of the brick is much larger than the Poisson's ratio of the mortar. So when we apply a compressive stress on the brick and the same compressive stress acts on the mortar now wants to expand less than the expansion of the brick. So what happens when tension part explain uniaxial compression in the vertical direction, the brick goes into a state of triaxial compression. So the dangerous state of stress is basically this biaxial tension. So basically the mortar is now in tension. And I'll show you how this plays out in the failure of the brick. So what we did to understand the failure of the brick is we made several masonry assemblies with different aspect ratios, just to understand, of course, what would happen when you even vary the aspect ratios. Masonry with different arrangements of head joints and bed joints. So we did, they made these different masonry assemblies, and then we tested them. Now, before that, what I wanted to show you is how masonry behaves in the stack bonded. Yes, well, okay. Very distracted by the comments. So when we actually look at the behavior of masonry and we apply a compressive stress on this, and let me go back to this case of the soft brick and the stiff mortar, and the two cases that we considered, the strong mortar case and the weak mortar case. Now, what we find is that if you remember, the brick had a compressive strength of 15 megapascal. The mortar strength for the strong mortar was 30 megapascal. What we find is that the compressive strength of the masonry, this is the compressive behavior of the masonry. The compressive strength of the masonry is actually lesser than the compressive strength of both the brick and the mortar. This comes as a surprise because normally when you work with composite theory, the composite would have a strength which is somewhere in between the two constituent materials. But what we find here is that the compressive strength of the masonry is actually much lesser than the compressive strengths of the two materials that were used. Now, similarly, if I go to the stress strain behavior of the masonry, stacked bonded masonry made with the weak mortar, the same thing happens. Now, again, the compressive strength of the masonry is actually much smaller than the compressive strength of both the brick and the mortar. So now, the other thing that we notice is that for a very large increase in motor strength, that is when I went from strong to weak motor, the strength of the motor actually tripled. It went from 10 megapascal to 30 megapascal. The masonry strength that increased when going from weak to strong motor case in masonry was very small. So there's only a very small gain to be achieved in using a strong mortar when you're dealing with a very soft brick. Now, we also looked at the failure in these things, and what we notice, which is not surprising, is now this is a stack bonded masonry. When we start loading it, is where you start. This is the stress strain behavior in compression. This is a stack bonded masonry. Now, when I apply compression on it, what we find is that, remember, in this particular case, the brick, sorry, let me just go back here. So the stress state in the brick, this is the stress state that we're looking at. The brick is in a state of triaxial compression. The mortar is in a state of biaxial tension and uniaxial compression. So now, in that case, if you look at it, what happens? The crack, this is the interface between the brick and the mortar. So the crack starts right here. That's where the tension is there in the mortar. The mortar splits first, and then that drives the crack into the brick. The crack then grows, and what you see is that basically you get splitting of the masonry. Basically, the masonry starts splitting because everywhere the mortar is in a state of biaxial tension, or it's basically in tension in the plane of the joint. So it's basically in this plane here, the mortar is in tension, and that causes splitting of the mortar, and that induces cracking in the brick. And what you see is the failure is produced by the splitting cracks that run all the way through the height of the masonry. So the failure that comes about, and this is for the case of the weak masonry that we are looking at here, and irrespective of whether we're looking at weak or strong masonry, the stress state is such that the tension cracks are driven by the mortar. Mortar basically is locked in the state of very high tension, in plane tension. The mortar splits, cracks. The minute it cracks, it basically forces cracking in the brick, and that basically drives this vertical cracking in the masonry, and that is one of the modes of failure that we observe. The other thing we observe is that there is a localized failure that happens. Basically, the brick actually, which is in a state of triaxial compression, compresses here, and it basically experiences localized compressive failure. It crushes over there. So there is a crushing also that happens. So there's crushing mode of failure that happens in the brick, and there is splitting perpendicular to the joints that we observe in this masonry assemblies. Now, when we go to this masonry that we had made with different aspect ratios, if you remember, I told you that we had made these masonry assemblies with with different aspect ratios. Now, every time we tested any of these brick masonry assemblies, we were looking at the strain contours, and for that we were using digital image correlation, which basically gives you a surface map of displacements. And from the displacements, then you can construct the state of strains. Now, this is basically one particular arrangement of bricks where we have a head joint and a bed joint. Then there is masonry, another bed joint and head joint, and so on. And that pattern basically repeats itself. The aspect ratio is 1. That means the specimen, if you look at the cross section of this, it is 1:1. What we find is that in this particular masonry specimen, there is a lot of tension that is produced even in the head joint here. And that tension that you can see here, we plotted the strain along here, and from there we basically simply calculated the stress. We find that very heavy tension is produced in the mortar, which we expect. And that mortar is the tension in the mortar is what causes splitting of the brick directly below the head joint. Now, even when we went to higher and higher aspect ratios, anytime we had a head joint, we found that the tension was very, very high right here. So this is where the tension is very high, which led to a cracking in the brick directly below the head joint. Same thing here. So wherever we are seeing head joints, we're finding that this tension that is produced in the mortar, that leads to splitting of the brick directly below the head joint. So these head joints act as stress risers and lead to vertical splitting of the bricks in the masonry. The next, we also study what stress transfer takes place between brick mortar to shear. How much shear transfer takes place? And that's again very important when we start looking at the in-plane behavior of masonry. For that, we used a very simple triplet test. And the triplet test, what we do is we basically have three bricks, two bricks which are at one level, and the third brick set. So as you can see here, this brick is a little offset in height. Now this forms a triplet. So you have two bricks at one level and then the third brick which is offset. Now, if you put this assembly on the floor, let's say, and you basically push down on the middle brick, what will happen is you'll induce shear right in this motor interface, and you'll also induce shear in this motor interface. So this setup allows you to study the shear transfer that would take place from this middle brick as you push down on the brick to the two side bricks which are sitting on the sides. So this allows you to study the shear transfer that is taking place across the motor interface. And remember, motor is an interface that is between the bricks, and that's enabling stress transfer between the brick units. What we did, which is a little interesting, is we basically did a modified setup where we were able to apply confinement on the brick. Now, this confinement is, we had a setup where basically we put channel sections on the sides, and by tightening the rods, which were instrumented, so we could actually measure the kind of the amount of stress we are applying, we could actually subject this triplet arrangement to a confinement stress and then do a triplet shear test. Now, this is what the typical result that we get for the triplet test. What are we measuring here? We are measuring the shear load or this load that I'm applying on the middle brick and the slip that happens in this brick. That's essentially what we're measuring. Now, initially, when the motor is intact, there'll be no slip. As this motor assembly or this motor interface fails, this interface also fails, the middle brick will start slipping relative to the other two bricks. Now, this is what the load global slip or the slip of the middle brick looks like for three levels of confinement. When I have no confinement, you get a load shear load versus slip response that looks like this. And as I increase the confinement, you see that a larger amount of shear can be transmitted from the middle brick to the two side bricks, which means basically the shear transferring ability or the capacity of this mortar increases with the confinement that you apply. Now, why is this even relevant? If you look at the confinement, and in a typical masonry wall, the confinement would come from the vertical loads. And the shear loading that we're talking about, and we're trying to evaluate the shear stress transfer, this is something that you would expect when you're looking at the in-plane behavior, in-plane shear response of a masonry wall. So we studied this further, this masonry triplet test, and we looked at the failure that happens. And invariably, what we saw was the failure happened at the interface between the brick and the mortar. But with increasing confinement, the failure started happening in the motor itself. Now, what I want to show you here is that shear failure at the interface is actually quite a complex phenomenon. And what is plotted here is a double Y graph. Now, this is what we typically get from a triplet test. Here, the axis on the left shows you the shear load or the load that I'm applying onto the triplet on the triplet. And on the right-hand side, I'm actually showing you the confinement stress. Now, you may say that, well, you're applying a constant confinement. Why would the confinement change? What we applied was an initial confinement. So I tighten the screws and I basically apply a fixed level of compression on the triplet. Then I start doing my shear test. So the initial confinement is this value right here. That is when before this test starts, when the slip is 0. Then when I start pushing the middle brick, you see the slip starts to increase. Slowly, the middle brick starts to move relative to the other two bricks. As that happens, the shear load actually picks up. Now, the shear load picks up because now there is initially what you see is a nice linear response. This is because the shear interface is getting engaged. The bond between the two materials is getting engaged, and a larger and larger amount of shear force can be, or stress can be transferred across these two bricks um, up until a certain point when you see a sudden change in the slope. Now, this change in the slope, if you notice, with the change in the slope, the confinement starts to increase. So what's happening here? Here is where a crack starts to form at the interface between the two bricks. As the crack starts to form, the slip starts to increase dramatically. Just you see here, but the load doesn't increase so much. And or I should say the slope at which the load versus global slip, the slope of this line, that sees a change. And this is very typical of crack forming in any brittle material or quasi-brittle material. Then eventually you see what happens is that the load actually levels off. So load levels off at some point. And at that point of time, if you look at the confining stress, the confining stress also becomes constant. So what is happening here? Why is the confinement stress increasing? As the crack forms in the interface, the crack that is formed is actually a rough crack. And as the rough crack starts to slip, when the two rough crack faces start to move relative to each other, dilation is produced. So whenever you have two rough surfaces that are slipping past each other, you will see an expansion that takes place. And that's exactly what's happening in this part here. So here the crack is forming, and as the crack is forming, you see that the confinement starts to increase. That's because as the two crack is forming and the slip starts to happen, the rough crack faces start to move against each other. There's dilation that's happening, or basically the two faces are being pushed apart as the crack faces are slipping past each other. And as they're being pushed apart, because we have kept this threaded rod assembly, the confinement starts to increase, because now the bolted setup, suddenly that starts seeing more tension. And so you see more and more confinement up until a point when the load levels off and the confinement also levels off. So what's happening at this point? The crack has completely formed at this point. Now, basically there is no bond. It's completely cracked. Now, the crack surfaces, as they're slipping past each other, there's a constant amount of expansion that takes place that produces a constant amount of confinement in the system. And at this point, the resistance is coming purely from frictional resistance between the two faces that are formed. And therefore, you see, because the confinement is a constant, the frictional resistance is also constant. So this is basically what's happening in a typical shear test. So in summary, when I talk about masonry, I have a tensile splitting of bricks that we see. That's because of the biaxial tension state that is produced in the mortar. And we see tensile splitting along the head joints. In the mortar, shear and compression, we see interface cracking, which happens between the brick and the mortar interface. It's a dilational response, which means as the shear crack forms, or as the cracking happens between the brick and the mortar interface, there's expansion that takes place. And the final resistance is given by the residual frictional resistance between the two materials once the crack is formed. So now I'll quickly run through the modeling of this. So with this data now, we developed a material model, which is also called the micro model, micro approach, where what you do is, if you have a masonry assembly like this, you basically assume that the mortar interfaces are infinitesimally thin. Basically, you expand the bricks so that the brick, this mortar interface essentially disappears and it becomes infinitesimally thin. This is now called a joint. And everything in between inside this is called a unit. This unit is basically now made up of this brick and some part of the motor here, half of the motor here, and half of the motor here. And what is the role of this joint here? this joint has the same properties of the interface that we have obtained from our test before. Now, because in this so-called pseudo assembly that we've created, we are basically creating a unit that consists of the brick and the mortar. We basically come up with the effective properties of this unit, which is an effective property of combined brick and mortar. So this is a very well-established approach. And then we get into this pseudoplastic kind of a formulation, except now we treat the brick as if it is elastic and perfectly brittle material, which fails by cracking. The interface between the bricks, which used to be the mortar, is now labeled as which is now modeled as this infinitesimally thin layer, which has a finite shear versus confining stress kind of a response. And basically, we model the interface as a more Coulomb frictional type of a material with a tension cutoff and a compression cap. And all of these parameters that you need for the model can be obtained from the, excuse me, from the shear test that we perform. And when it comes to the head joints, we can basically put a vertical gap between the two brick elements where we expect to see splitting between the bricks. Now, with this model, we were able to predict the response of different masonry assemblies. So if I can just move this here. So here, what we have here is a masonry assembly of a certain height and width, where the which is made up of brick of 1 GPa, which is what we tested in our program, a masonry strength of 5.8 MPa, and this is the masonry made up of the weak mortar. Now, when we go with trying to predict the response of this masonry structure with an H over D of 0.75, which is basically like a squat wall subjected to a compression of 0.5 MPa. And if I try to get the lateral response of this, this is what this is the what is predicted by the numerical model. And we can also actually predict the failure in this masonry unit, where in this particular case, there is onset, basically it fails in flexure at one side, and with continued loading, we can actually see when the diagonal crack would start to form. It's a squat wall that basically fails in shear. A shear crack forms through this. We can actually now simulate the damage that happens in the brick all as I push the wall all the way up to failure, where the failure of the wall happens because of this shear diagonal cracking that forms in the masonry. Now, this is the diagonal shear cracking in the masonry that is predicted for a squat wall made up of brick with 14 MPa strength. This is the brick that we used in an experimental program. The low strength mortar made up of soft brick of 1 GPa stiffness. Similarly, we can also predict the flexural cracking response of the same masonry. What do I mean by saying flexural cracking? If I take the same masonry wall, which is subjected to 0.3 megapascal compressive stress, but now my H over D ratio is 1.5. So basically now it's getting taller compared to its width, and apply the lateral force, we see that the failure pattern changes completely. Now, this particular wall fails in flexure. It fails in a flexural mode. The final mode of failure is by crushing a brick at its toe, which is basically the far end from where I apply the lateral load. Yeah. So with this now, we were able to establish the modes of failure of masonry walls, which are subjected to different levels of compressive stress. This should be levels of compressive stress, not compressive strength. So if a masonry wall is subjected to a low compressive stress, this 0.01 refers to the value as a percentage or as a fraction of the compressive strength of the wall itself. So we went from something like 1% of the compressive strength of the wall to a compressive stress in the wall, which is almost 20% of the compressive strength. Now, if most masonry walls have vertical stress, compressive stress, which comes about from the load that is bearing on them. And typical numbers range between about 10% to about 15, maybe 20%. So this is more the typical range of compressive stress carried by most masonry walls. Now, the other important thing about masonry walls is the aspect ratio. So we went from 0.5 all the way to 1.5. Now, for a very squat wall, which is the aspect ratio is 0.5, at a low compressive stress, low vertical stress, we see a sliding type of failure where the wall basically simply slides off from the bed joint. When I increase the aspect ratio, I get into a flexural mode of failure. But when the wall is squat and the compression is high, for the squat walls, as the compression increases, we also get a shear mode of failure. Shear mode of failure where you have a diagonal crack that runs through the masonry. Now, just to recap, if you remember, when I presented the photographs from the failures from the masonry, one of the buildings had diagonal cracking, and that happens in squat walls, aspect ratio 0.5 and 0.75 at moderate to high compression. 20% of the compressive strength of masonry is considered fairly high level of compression. But the minute we make the wall slender, the wall fails in flexure, which is basically produced by crushing of the brick. Now, after we identified these modes of failure, next thing was to predict the cyclic behavior, where basically we now started working on looking at the cyclic behavior of this masonry subjected to this cyclic ramps, and the predicted responses of, in this case, basically a squat wall, which failed in shear. And this is a typical response that we got from the cyclic behavior. It's what we call a pivot type of behavior, where you see that most of these load cycles are pivoting at a point. Now, this is something that is predicted, where we are starting to see a pivoting behavior. Experimentally also, data that's available basically had a pivoting type of response for shear walls, which basically failed in shear, sorry. Then the walls that failed at sliding, which are squat walls with very low levels of compression, the kind of failure that we get looks like an elastoplastic kind of a response. The reason I'm even bringing this up is because at some point we'd like to be able to do parametric analysis where I can parameterize these, and then I should be able to run simulations for different types of walls. Now, when we come to flexural failure, so here is a wall that has a which is basically slender, where the height is bigger than the width, and subjected to a moderate level of compression. What we get is like a hardening plastic kind of a response from this particular wall. So now, when it comes to cyclic behavior, also we are able to handle and essentially see that the cyclic behavior of these masonry walls, depending on the level of compression and the aspect ratio, falls into one of three categories. It fails in shear, it fails in flexure, or it fails by sliding. And each one of them has a very typical cyclic response. So that is the material part of it. And we seem to now have material models that can accurately model the cyclic response, which are built from ground up. I do realize I have not presented to you in detail about the plasticity modeling, plasticity coupled fracture model that we did for the masonry. But hopefully I presented enough to help you understand that from material tests, we scaled up and then we developed these calibrated models for masonry. What is different about the models that I presented here is that these models work for soft brick masonry. So they are basically, they work when the brick is softer than mortar. And how much softer? In the experimental program that we did, the brick had 15 megapascal compressive strength, but a stiffness or Young's modulus of only 1 GPa. Mortar, which the weak mortar that we produced, the mortar which has 1:6, one sand is to 6, one cement is to 6 sand, had a compressive strength of about roughly about 15 GPa, excuse me, but Young's modulus of about 10 GPa. So the mortar, even in the case of a weak mortar, is 10 times stiffer than the brick. Now, coming to the ground motion generation, and we decided that we would look at the Gujrat, the Bhuj earthquake for a case study. Now, in 2001, as you all know, there was a massive 7.6 magnitude earthquake that struck the Kutch region. The sad part of this is that there are no strong ground motions that are available. None were recorded. We did not have any recording stations here. We didn't expect an earthquake, and so there are no ground motions that are available. So if you really want to do any study, you're basically helpless, because only thing that's available or was available to us at that time were PGA values. Peak ground accelerations were available from 13 stations. That's it. So now if we really had to do an analysis, it's essentially like trying to wag the dog by its tail, where now using these 13 PGAs, somehow I have to reconstruct the ground accelerations. But of course, when you're trying to peg something only on PGA, there are a whole bunch of other variabilities that come into play. So we had to capture those variabilities if we really wanted to do the vulnerability assessment. And of course, if you ever want to do nonlinear time history analysis, you need full suite of ground motions, which we did not have. Now, the Kutch region, or if you look at Gujarat, it's a very interesting state. It has actually all three zones, and this is as per the old IS 1893. You have a certain portion, a major portion of Gujarat in zone 3, a small portion in 4, and this portion, Bhuj, which is located here, is actually in zone 5. And subsequently, of course, a lot of crack fault maps were developed, a lot of faults were identified, and the major fault which was responsible for that earthquake was identified, which was basically something that was to some extent helpful to us. Now, how do we go around estimating ground motion? So one thing we could have done is that we could have actually taken existing ground motions and scaled them. But then there are issues associated with scaling of naturally occurring ground motions, because earthquake ground motions captured in different regions have different frequency contents and other things. So we decided that we would actually generate synthetic records of ground motions. And for this, again, there are different ways of doing it. And what we decided to do was to use the modified stochastic finite fault model, which is available in the XSIM software, which allows you to do that. The only issue here is that the data that's required to generate ground motion records with this, there's a lot of data that's needed. The data that's needed is beyond what most civil engineers would even have access to. So here we've, and just to tell you about stochastic finite fault model, what we do is we take a fault and we divide it into smaller subfaults. And basically each of these acts as a source. And the simulated accelerogram then is basically made up of by combining each of these source points on the finite fault surface, the ground motions or from each of the source, the ground motions is simulated, and the final record is a sum of all of these records that you find. Now, in this particular model, one of the key things is the seed, which would be the seed point, and that can be treated as a random variable. So I can generate multiple records of ground motions just by varying the seed point on the fault surface. But of course, details of the fault surface itself was beyond us. I don't have much of knowledge on this. So here, basically, we were working with geophysicists and helped to basically get the source parameters for generating this synthetic ground motions, which would help us run that the stochastic model that we had on our place. So all of these parameters were given to us by the geophysicists. And from there, then we were able to generate the acceleration, the ground motions at the rock level using the fault data that was available to us. And because we only had PGA values, so we had the recorded PGA values, 13 PGA values at 13 towns in Gujarat. The first thing was to match these things at the rock level. And that is what we did. And we got a fairly good match of the ground motions, except 2 or 3 stations, which had some issues with with the way some corrections were done to the data over there. Next thing is that the ground motions that were simulated at the rock level were then basically using the soil amplification functions. The surface, ground motions were predicted using the soil amplification data. Again, this was given to us by the geophysicists. So we got the soil amplification data for each of these towns from the geophysicists. And then we use this to come up with a suite of ground motions. And for each location, we basically generated 30 ground motions. Each ground motion basically had this random seed, which allowed us to produce different a suite of ground motions. And then we got the rock level motion, and then using the soil amplification function, we then projected it to the surface. So this is sorry. These are the response spectra for four of the towns that were located in zone 5. So from there, now you can start playing all these games where you can generate the mean spectrum, the maximum considered earthquake, and the DBE as given in our. Incidentally, sorry, the black and the dotted line are the maximum considered earthquake and the DBE as given in IS 1893. And what you can clearly see is the mean spectrum itself, and most of the spectra were lying way above even the MCE values for this earthquake. Next thing is now we have the ground motion spectrum with all the variabilities. Supposedly, we've captured the variabilities. The hitch there is that, of course, we were pegging everything to the PGA. So we had only the peak ground acceleration, and we were trying to match that and predicting the ground motion using the finite fault model. Now, the next thing is basically we have the simulated responses that we are able to do for different walls. So here, wall 1, suppose I take with the lower axial load. So when you take a wall which has a low axial load, it will fail in flexure. It fails by pivot model. So we basically calibrated a pivot model to this response. Take another wall which basically has a higher level of compression on it. So higher axial load. This fails in shear. And again, this is calibrated with a pivot type of model that you see around here. Now, the clear states are identified from the model. One is that of cracking. That comes from the envelope curve. This is the envelope curve. So the masonry cracks here. This is identified as a strength state, maximum stress. And this is the collapse where the masonry fails. So these are the 3 limit states that we have. Cracking. Cracking happens very early in the response. Then you have the strength, which is the maximum resistance, and then collapse, where basically it fails. And you get essentially after that, there's no more load resistance. So now to bring in uncertainty in the pair calculation. So the first part was modeling the response. We were able to do that mechanistically. Then modeling the cyclic response, which we did. Then we fitted parametric models to the cyclic response. But the most important thing is to consider variability in the material properties. Now, to do that, we basically considered the important material parameters, and we varied the parameters about plus to minus 20% of the mean to see which of these are sensitive parameters. And we found that when you predict the capacity curve, the monotonic push curve, for a pier failing in shear, it is sensitive to cohesion, friction angle, and Young's modulus of the brick. Similarly, piers failing in bed sliding, it depends upon all 5 parameters, and those failing in flexure, it only depends upon the Young's modulus of the brick, or these are the sensitive parameters. Then the thing is, how do I go around sampling these material properties? Because if I want to do something like a Monte Carlo simulation, there are way too many variables. I have ground motion variables, and then of course the material variables. And there are 5 material parameters that we had, which is the cohesion, friction angle, Young's modulus, Poisson's ratio, and residual friction. If I start varying them, I would run into millions of data sets. So what we decided to do is to use the Latin hypercube sampling, which allows us to create random sets And essentially, with the Latin hypercube, we are able to create a smaller data set, which basically, through this random sampling, allows us to capture essentially a good high level of accuracy while reducing the sample size. So with that, then we were able to run the simulations for 10 brick unreinforced masonry piers, considering the variables and the material properties that we got from the Latin hypercube samples. And simulations, we pulled out 10 PGA levels and then ran our simulations for the nonlinear time history analysis to develop the collapse fragility. And this is what the seismic response of a URM unreinforced masonry wall would look like. And what I marked here is the displacement as a function of PGA. So what we were doing here was varying the PGA, and for each PGA, we basically created about 10 ground motions. And for the ground motions, then we had the material samples that we got through the Latin hypercube and run the analysis for each of these. So as we increase the PGA, you can clearly see that the displacement, that is the maximum displacement experienced by the pier, that increases. Now, what is marked on here is the dotted line here represents the cracking limit state. This dotted line here, this dashed line here, represents the strength limit state, the maximum resistance, and the solid line here is the collapse limit state. And you can see that it actually at a very low value of PGA, most of these walls, which failed in shear under the static loading, most of these walls were actually cracked at a very small value of PGA. Again, at a very small value of PGA, most of the walls were even pushed beyond the capacity limit. And at a PGA value of around 0.1 or so, you see that most of the walls had also failed. So it doesn't take a whole lot of ground acceleration to fail these walls, which would otherwise exhibit a shear type of failure under static loading. That these, all it would take is a very small amount of PGA of around 0.1 or so to produce failure in these walls. Same thing with the PGV. Now, what about a wall that fails in flexure? This is a wall that is little, which has an aspect ratio which is greater than 1, say 1.5, and has a moderate amount of compression. Same story repeats itself. So you see that the walls, even the flexural wall would crack at a very small value of PGA. It would even reach the capacity, the strength limit at a low PGA. And by about 0.1 or so, you'd start seeing collapse of those walls as well. So from here, then we can construct the seismic fragility curves for the three limit states, the cracking, strength, and the ultimate, as a function of PGA. And what we find is for wall 1, which is a wall that failed in flexure. That means this is a wall which has an aspect ratio which is greater than 1 and is subjected to moderate level of compression. Here, what you see is that if you go to a very small value of PGA, basically you essentially have a probability of failure hitting 1, which means that most of the walls would be cracked even for a very small jolt that you would get at a very small PGA value. If you look at something like PGA of 0.05 G, you'd find that about 40% of the walls would have failed. They would basically be essentially would have no capacity left in them. They would essentially have failed. Now, by the time we come to a value of 0.2 or so, 0.2 G, which is actually quite severe, most of these walls would have failed in this thing. And in shear, the walls that would fail in flexure would essentially have failed. The same story would repeat itself for this other wall that actually fails in shear. You find that at very small values of PGA, the walls would be cracked or they would have reached their capacity limits. And by about 0.2 or so, essentially all the walls would fail in or would have exhibited failure. Now, the ground motions from the towns that we had in zone 5 of Gujarat had PGA greater than 0.1 G. So we were basically sitting somewhere around here to the right of this. So if you look at 0.1 G, it would indicate that almost 80% of the walls, which are basically flexure walls, would have failed. Similarly, if you come here at 0.1 of G, about 30 to 40% of the walls which were designed to fail in shear would also fail. So our analysis is predicting that basically we would expect to see very high failures in walls which are subjected to in-plane shear loading under an applied compression. Yeah, so now we can do the similar plots with PGV. You can play around with the parameters and look to see when you get a high probability of failure. So yeah, so from this whole study, what we've managed to do is first look at the material that we're dealing with. When we started playing around with the material, we realized that we cannot use the material models that have been developed for masonry and apply them directly to our case, because the masonry that we're dealing with in India has exactly the reverse properties of what everybody else has been using. And that is, we're dealing primarily with what we call soft brick masonry walls. The brick is very soft. Its stiffness, its Young's modulus is very low compared to mortar. While its strength is moderate to high, its modulus, it's very, very soft. And what that does is it completely changes the stress state in the masonry compared to what we are expected to believe when you're dealing with high stiffness bricks in masonry. What we find going further is, if we consider bringing the variabilities and all these, we find that different parameters of the material model influence the behavior of walls differently. Now, when you're looking at a masonry wall, there are three types of walls. You have a shear wall that fails in shear, you have a wall that fails in flexure, and you have a wall that fails in sliding. What distinguishes these three walls is the aspect ratio. What is the height or the height to the width ratio of the wall? And not surprisingly, if I increase the aspect ratio, that is, if I make the wall slender, it fails in flexure. If I make it squat, it fails in shear or in sliding. The other parameter that comes into play is the level of compression. Now, the level of compression on the wall is dictated by the vertical loads that are coming on the wall. Remember, more often than not, these walls are load-bearing walls, which means there is a slab or something sitting on top of it, so there's a vertical stress. The typical vertical stress in masonry ranges from anywhere from 10% to about 20-25% of the compressive strength. These are the loads that are coming about from superimposed load on top of the masonry wall from whatever elements it's supporting. And primarily these walls are used as gravity load-bearing walls. They're hardly, if ever, designed. Most of these walls are not designed. They are what we call non-engineered construction. And the issue with these walls now is that we find that overall these unreinforced masonry walls are very vulnerable to seismic or lateral forces. Now, fragility of shear walls, that is, a wall that would fail in shear, is actually lower than that for flexural walls. The flexural walls are much more vulnerable. And the cracking limit state, or this walls would basically crack at very low, very small values of PGA. At 0.1 G of PGA, 70% of the walls would basically collapse. So, and what happened in Bhuj was that they were seeing recording PGAs of 0.2 G and higher. So, not surprisingly, entire towns were flattened. Most of the construction there was load-bearing masonry, or in some cases they had infill. So they had non-engineered structural frames with brick infill. All of those basically failed, and so most of them had either reached their capacity, the strength limit, or they had actually collapsed. So, and the region experienced structural damage corresponding to intensity I level of 6, indicating deficiencies in design and construction practice. Basically, this is the sad story about the construction in India, where a lot of it is non-engineered construction, and it is extremely vulnerable to lateral loading. So with that, I'd like to thank you for your attention, and maybe now we can have questions.
Thank you, sir, for your wonderful session. It was very informative. and I believe that it will be very valuable for our participants. Now, sir, if you agree, we can take up the questions.
Sure. Yeah.
Yeah. Sir, one of the participant wrote, is the modulus of elasticity strictly applicable to brick as it is not an elastic material?
Yeah, I saw that question. It kind of came up when I was presenting. So yes, now when you look at any material, right, even concrete, now most of these materials will behave in a linear elastic manner up to a certain point. They are not inelastic to start with. So if you look at, let's say, concrete, it's linear elastic up to about 50% of the compressive strength. What does that mean? When it is linear elastic, all the elastic properties that you get for elastic materials are applicable. So it would have a Young's modulus, it would have a Poisson's ratio, everything holds, right? Same thing for brick. The initial response is linear, and those are the elastic properties that I'm referring to, the initial stiffness.
Yeah. Sir, another question is the compressive strength. Is the compressive strength of brick masonry lesser because of improper bonding between them?
I'm sorry. Can you repeat that question? Maybe I can read
Yeah.
it.
Is the compressive strength of brick masonry is less because of improper bonding between them?
Huh.
They are
Yeah.
asking
So,
like a unit and mortar, there is not proper bonding. Is it
yeah,
the
yeah, yeah.
reason because of the less compressive strength?
Yes and no. I mean, the thing is, uh, if you talk about improper bonding, that opens up another uh, can of worms dealing with quality. So even if you have perfect bond, that is, you are doing a very meticulous job, a very careful job, even there, you will get a splitting kind of failure, which happens because, so okay, let me backtrack a little bit here. What we found is that the masonry strength was lower than the strength of the brick and that of the mortar. It is always lower than that. And this goes counter to the principle of composite mechanics, because in composite mechanics, what we say that when I have two materials and I mix them together or combine them, the combined material will have properties that is somewhere in between the two materials, right? That's typically what we expect
Yeah,
from
that is the
composite
stress
behavior.
strain. If you draw, the top one will be the brick, the below bottom one is the mortar, and the in between there will be the
Masonry should be there. We were
yes.
not seeing that. We were seeing the masonry was actually lesser than this. And the
Mm.
answer to that lies in the fact that the stress state that is produced, the stress states that are produced in the material, because of the mismatch in the properties, that leads to a premature failure, tensile cracking, which leads to a very early load drop and basically lower stress. So the two materials are basically, because of the massive mismatch in Young's modulus, the Young's modulus of brick was 1/10 of the Young's modulus of masonry of the mortar. That was leading to very early splitting of the brick and basically just leading to a very premature failure.
Yeah. So just now one of the participant asked about the interlocking masonry. So interlocking brick is also
Yes. See, these
best
are
used.
correct. Interlocking masonry and all of these things are modern engineering concepts. I mean, these are things that can be studied. The focus of what we are looking at is this run-of-the-mill house that is built in most of the rural places. And how is a house typically built in India today? It's a non-engineered. So
Mm.
forget about somebody bringing a locking brick or being even aware of it. What they typically do is that they basically go to a mason, they procure some bricks, they'll construct some walls, and they'll put a slab on top of it. Right? This is most of the construction that is happening in India. It's non-engineered, using local materials, and everybody tries to basically drive down the cost. So, and you go with something you're familiar with. And in India, we're very familiar with masonry. Everybody constructs with masonry. So
Yes.
you go down to the rural side, you'll find hundreds upon hundreds of these non-engineered masonry construction. In fact, the older masonry construction is perhaps better because two things. They did not skimp on the material. The walls were usually thicker. Two, the bricks were hard fired.
Mm.
So they actually use good bricks. Today, what is happening is that we are not hard firing our bricks. The bricks are of very poor quality. They're very soft. On the other side, cements have become stronger. We went from OPC 33 grade to OPC 53
Yes.
grade. So what is happening is the quality of the brick has gone down, the quality of cement has gone up. So mortar has become stronger than the brick. And this
Yes.
is the reverse situation we're finding. And a lot of construction in India today is of this form, where they've used a soft brick and they've used a stiff mortar or strong mortar. And now you will not find anywhere in literature or even in books on how to model the behavior of this, because everybody basically presumes that brick is stiffer than mortar. That's typical masonry for you. And that's how it has been for century, for millennia. In fact, that's how we've made masonry. So we had to essentially invent the whole mechanics to be able to model it first and then try to predict its behavior.
So then, how what do you think? Like for the comprehensive in the big masonry, as the latest IS code included lately that is depends on the comprehensive strength of brick, FB, and comprehensive strength of the mortar, and then one
Correct.
expression was given. So
Correct.
those expressions are still valid for that.
Yes, what they've done is they've actually empirically calibrated the full range of. So they've tested lot of motors, lot of bricks.
Mm.
From there, they have empirically calibrated the compressive expression for the compressive strength of the masonry.
Yes, yes, sir. Sir, one more question came like if you use the fly ash brick, then instead of burnt clay brick, then will that be also considered as soft brick?
Yeah, fly ash brick. If depends on the method of manufacture. Fly ash bricks
Mm.
also, there is no consistent method of manufacture. You can end up with a soft brick, or you can have a stiff brick. Depends totally on the method of manufacture.
Yeah. So that's all I got now. Dear participant, if you have any queries, maybe you can send it to me later on and I'll forward it to sir and I'll try to address all those. And thank you, sir. Thank you for a session. Probably, sir, our coordinator Robin Davis sir is online. Robin,
Good,
sir.
good evening. Good evening, sir. This is Robin Davis. I am also one
Hi.
of the coordinator. And thank you, sir. Very nice presentation. Then this is first time I am listening to you. So thank you, sir. And I have a couple of questions. Will it be possible, sir, to see the slide once again?
Just one moment. Where is my share? Okay, I think I'm sharing it. Yeah.
Yeah. Thank you,
Let
sir.
me
So
let me go to
if
the full screen mode. Yeah. Mm.
yeah, that conclusion, that slide, no, some.
Yeah.
So just I'm trying to understand that fragility of shear wall is lower than flexural walls. So if you
Yeah.
see that curve,
Yeah.
uh, so because it is coming, it is failing first. Can you go to that
Yes.
fragility?
So if you actually look at, here is the fragility curves, right? So you look at the
Yes,
flexural wall. Okay, so this is the flexural wall, and this is the shear wall, right? So
yes,
it's a little hard to tell, but you can see that the shear wall up to about 0.0506, right?
yeah,
No walls would fail, and whereas here the failure starts much earlier.
yeah. So you see, it is initiating at a higher PGA.
Yeah,
Maybe
yeah.
right.
Or the probability of failure is going to scale up much more rapidly for flexure failure walls that fail in flexure. Right? You
Right,
see, it
right.
builds up very rapidly. This is the probability of failure, right?
Right.
Yeah.
Another couple of questions. So one another thing, I think it maybe that we have to consider is that this out of plane mode of failure, right?
Yeah.
I think most of the buildings, if you see, if you see that gable walls and all, many
Mm.
times it is failing in this out of plane. Maybe that kind of study can also be done.
Correct.
Uh,
Outer plane
but
is certainly, I mean, it is a valid mode of failure, and we do see that happen as well. The reason why we focus more on the in-plane mode is when you apply, let's say you have four walls which make up a room, right, or which make up
right,
a unit.
Right.
And you apply a horizontal force on it. The in-plane walls end up taking the load. Essentially, the outer plane is negligible. And what happens is the outer plane is, it collapses. It basically falls out of plane. It doesn't have much outer plane
Right.
bending
Right.
stiffness. So in what we were modeling, essentially we were looking at saying that, look, if you have an outer plane wall, discount its contribution and only take the in-plane walls and then go to the prediction of the in-plane, the response of a unit or a house or made up of multiple walls and so on.
Right. So
Right.
it is not contributing to the load in
Correct.
that direction.
So an outer plane mode of failure is equally dangerous. Actually, you have these wall collapses that happen when you go
That
into
also
outer plane.
may create some life
Correct.
risk.
So that, yes, that it is equally fatal, but it doesn't contribute to load resistance. That's why we didn't look at it.
Right. And can you go to that fragility curve that you are before fragility curve there is a displacement. Yeah.
This one, right? Yeah.
Yeah. I'm just wondering what is that. So if you see each and every point, and there is a line which shows some variation in the response. Is
This
it
one, right?
is
Yeah.
it that
So
due to the
material variation.
right? So it can vary that much.
Oh, absolutely. So here, what we have is this is the case of a wall that fails in shear, and we plotted PGA. For each of the PGA, we had done simulations, right? And we had considered the material variation in there.
Right. It is
Right.
clear. And you were mentioning that stochastic finite fault method.
Yeah.
Yeah. Which is that software?
XSIM is the one. This is the one.
Right.
XSIM. Now, this is a very complicated model. If you never used it, I mean, these are all the input variables that you need. And to be honest with you, I really don't understand all the input variables. So we were working with a geophysicist, Dr. Chopra, who basically guided us with all things. So
yeah. Anyway, that part is very difficult to make also, like generate also.
Yeah. So he.
Yeah. And one more.
So what we did is we did help.
Yeah.
No, one of the biggest issues that we had was we only had PGA values. See, that is the sad part, the irony or the tragedy of the Gujarat earthquake is that they only had PGA values at 13 locations. That's it.
Right.
And we don't, even today in India, we don't have adequate instrumented facilities from which we can record ground motions. Strong, certainly not the strong motions. Maybe in the Himalayas, we have a few sensors put up. But when this happened, everybody was looking at each other. There were no ground motions available.
Right.
So what do you do then? We had only 13 PGA values. So what we tried to do is basically, that's what I said. We were trying to wag the dog by its tail, where we have, PGA, we try to match the PGA, but then we know nothing about the record. So we were trying to create artificial records, but we then tried to bring in some level of sanity by bringing in this model, which is actually semi-rigorous. If you actually really get down to it, it's based on some proper physics. So we said, okay, we'll take the physics. We know the location of the fault. We know that the strike, the dip, and all these things precisely.
Right.
Then we will try to simulate from that using all this geophysical data and all that to see if we can predict ground motions.
Good. Yeah. Then one more question on that experiment of this wall. You are comparing with the numerical results.
Yeah.
Where some cracks and all. So for example, this. Yeah. Can you go to the previous one? Yeah. Here. Yes.
Oh,
this is
one.
fine. The before one. Yeah. The
You
last
want
one.
to say some? Oh, sorry. Yeah.
It is still showing shear wall. Okay, this is also fine. Now this is you are getting from the model, no? That colored thing, that contours are from the your finite element analysis.
This one. Okay. I think we are not looking. This is from the finite element analysis. This is basically
Right.
predicted.
Yes, yes.
This
So
one you
here,
use
what
the
is that?
LS
Sorry?
Sir, LS Dyna you have used, right, sir?
No,
For
no.
the
This
simulation.
basically no. This is not LS Dyna. This is TNO Diana.
Okay.
So this is something that came out of Delft University. We use that for
Okay.
all our simulations. So this comes from TNO Diana simulations.
Okay. And that here, when you if you see this one, it is very nicely matching this overall
Correct. Yeah.
this thing.
Yeah.
Yeah. But how is that comparison with experimental? That you
I
do that
forgot to show you. Yeah. So we did.
PIC.
No. So we did not. The experimental data for in-plane here came from someone else's test. We didn't do the in-plane. We did for compression, and we did material level tests from which we extracted material parameters, then put it into a finite element model for a structural scale, which is basically a wall. This is a physical wall of a
Right.
certain dimension, and use that to predict and match with the experimental data for that wall.
Right. So I was
Right.
just thinking that you did that small specimens, and then you could locate where is that first crack appearing.
That we could do. So the material level, of course, we had very nice control on the whole thing. So we were precisely able to locate where the cracks were forming,
Yeah,
and
very interesting.
yeah. So this then led to the material model, which then led to, which was then fed into a finite element model and a micro, what we call this is, let me show you the model. So this is basically, is a model that is developed by Lorenko in 1996, the micro approach, the micro modeling approach. And it's basically pseudo plasticity / fracture kind of an approach.
Yes.
But it requires a lot of material parameters, and those we were able to get from our material level tests.
Okay.
Right? So this is the plasticity model that they have. So it's basically a more Coulomb type failure surface with a tension cutoff and a plasticity cap.
Right.
A compression cap, sorry. Yeah.
So this other wall test, isn't it difficult? I mean, is it not that difficult?
Yeah.
That is why you are.
Wall tests are actually notoriously difficult to perform. So we actually got hold of data from other countries. The only problem there was that most of the tests that were coming from the other countries, the brick was invariably stiffer than the mortar. But then we were able to find a few tests where they had used weaker bricks. And so those are the ones that we use to calibrate our model.
Okay. And another one question, this say when you say soft brick, and our even in our country, the brick what we are getting in the olden days were actually stiffer one, right?
Absolutely. That's exactly what I said. So if you go to old masonry structures, you're better off because the brick was very stiff. They
Right.
used to hard fire the bricks. What is happening now is that now we are not firing our bricks properly. We are not pressing the clay enough. And we are not using good quality clay. So what we're getting as bricks in the market today are terrible.
Right.
That is the problem. And we're building houses with it. And what's worse is we're building load-bearing. This is compressive strength of the brick was 15.6 MPa, which seems fairly good, right? But its Young's modulus is barely 1 GPa. And if you look at the mortar, the 1:6 mortar, which is 1 cement is to 6 sand, gave me a compressive strength of 8.3 MPa, right? So that means the mortar is actually weaker than the brick, but it is 10 times stiffer than the brick.
Right.
Its
And
Young's
even it
modulus
happens
is,
even for a weak motor. This is the state.
correct. Absolutely.
Yeah, this is a new learning for me, sir. Thank you, sir. It is very eye opener. Thank you.
Sure.
Sir, one question I'm having, sir. I actually need your suggestion. Like, say if you're doing, if you want to find out the diagonal tensile strength, and if we follow the code like ASTM E519, for the diagonal compression test is given like 1.2 meter by 1.2 meter wall is to be tested.
Very
Now the
difficult
thing
to
is
do.
that constructing that kind of size of wall, and also if we see like if we are doing like 3 specimen, 3 sets of test for it, so it involves a lot of funding, and also the constructions this regard and all those are also all are involved. So
Correct.
what we can be suggested, like if we sample the test, if we do the testing for the one sample like we do for the shaking table, maybe the prototype model cannot be casted 3 times like for one particular sample. So can you do the testing for the one set or one sample and get the results? But also some material variability is also present for the masonry.
Correct. And these masonry tests are actually very notorious. Usually the variability tends to be very high. So,
Hmm.
and doing a good test on masonry itself is very difficult. Then to do tests on large scale specimens, and particularly the diagonal tension test, is not easy to do. So to get that experimental test setup working and get a good result from it takes some time and practice. So that is the tricky part of working with masonry. See,
Yeah,
the other
that
thing
time what
is,
happens?
yeah, unless you can create a need for it. Suppose you want to do research in this thing, then you have to create a need for it. The need for this is basically in this particular case, we have a large inventory of structures which are built, which perhaps have this soft brick in them. Now, how vulnerable are these? And these are very well vulnerable. That's the whole problem. And the worst part is that these are all non-engineered. Nobody designed them. We just got them built. 70% of building stock in India is non-engineered,
Hmm.
whichever form it's in, whether it is unreinforced masonry, unreinforced load-bearing masonry, or sometimes we even see reinforced concrete frames with brick infill. That's also used, but that reinforced concrete frame itself, nobody actually designs. I mean, if you look at construction that takes place, right,
Hmm.
70% of the cement in India goes into the unorganized sector,
Hmm.
which means the cement companies have no clue where it is being used. It's being used in the retail market,
Hmm.
where most of it goes into construction, which is not designed.
Yes,
So, but
yes.
they're getting built. These are your single unit dwellings, double unit dwellings, like simple construction, a typical family house. But even now, people have come to the awareness that yes, maybe having load-bearing masonry is not good. And I am seeing more and more people talk about saying that no, let's go with the concrete. They call it concrete pillars. So they say I want concrete pillars and put masonry in there. But who's designing the pillar? Nobody. It's just that the mason or the mistri
Mason.
comes and he says this is how I'm going to design. I'm
Yeah,
going to make it. I've designed 10 houses before. They have
yeah,
not
I have a lot
collapsed,
of
so you're
experience.
okay. Yeah. So, but it's okay as long as the going is good. I mean, vertical loads, no problem. Minute there is one horizontal jolt, we
Gone.
don't know how vulnerable they are. So we really need to see, first thing we have to do is assess the vulnerability of our existing stock, which means first evaluate what it is, right? I mean, what are we looking at? And 70% of our population of 1.4 billion is living in non-engineered construction. That is the scary part. So we need to assess how vulnerable these are, right?
Yeah.
And then we can start looking at maybe some methods of interventions and all these things. I mean, this is scary what the numbers we are looking at. So, and that is what triggered this study, where basically we got into it from a mechanics point of view, which is a very interesting mechanistic problem.
Hmm.
But then when we started digging deeper, we said, wow, this is scary.
Hmm.
So, plenty of things to do here. But
Yeah,
masonry is always a difficult material to work with.
yeah, yeah.
Yeah,
Yes, actually it happens. And also I'm surprised with that percentage, 70%. And even recently I checked with the statistics also. It is two numbers. It's a pretty large number. The
it
70% are
is.
the non-engineer. Initially I
Yes,
was thinking to search more in detail that whether this data has been updated or not. But I saw the no, same. So it is almost 70%. Earlier it was probably, I think 4 years back, I saw the data like 74 or 75 like that. Now it's 70%, but almost around
it's almost
greater
the
than
same.
70%. Yeah. So
Yeah,
in this way.
that is the scary part. That is
Yeah.
really the
And that's
scary
why I
part.
said, oh, we need this kind of programs. We need this kind of, expert talks. We need
Absolutely,
your sessions so that we can
absolutely.
pass on the knowledge to others.
No, what I'm hoping is it triggers something, as in,
Yeah.
we start looking at things that are of importance to us, right? And these are India-specific problems.
Yeah. Sir, could you please unshare your screen, sir? Stop sharing, sir.
Sure.
Screen. Okay, sir. Thank you, sir. Thank you for sparing your time, and thank you for your wonderful session.
Thank you.
Yeah,
Thank you all.
sir.
Yeah, if you have any questions, do drop me an email. I'll be happy to attend to those.
Sure, sir. Sir, we'd like to present you a small token of thanks, sir, from our side. Please accept it,
Thank you. Thank you. You're most kind. Okay. Thank you.
sir.
Thank you, sir.
Thank
Thank
you.
you, sir.
Thank you.
Thank you,
Thank
sir.
you.
Yeah, I'll be
Thank
in
you.
touch with you, sir.